What's up, guys? Alright, so today is the 22nd. Very late start today. I had other things I had to take care of. Thinking and stuff. That sort of thing. Anyway, so try to get at least a few hours in. So let's go ahead and pick up where we left off yesterday, and that would stop at line 110 and things do. Because we were doing a heavy brainstorming. I actually realized that my audio was all messed up because of having desktop audio enabled, and then I got the webcam, so it was like, then I quit using my headphones mic and I was using the webcam mic, and it's just like not, the mic on the webcam is not great. So looks like I'm gonna be back using this. I think everything works now. I did test it like on a recording beforehand, so everything should work now. The audio. So we're at line 110 in things to do. And we're going through these immediate race condition. Okay, this was for the this was to fix the fact that we might accidentally apply data that is not like actually next in line. So the way that we do this is actually, like, I was thinking not using the timestamps, I should have used the counter instead, but now I realize, at least I think anyway, that using the timestamps in tandem with the counter is actually the way to go, because the timestamp is so precise that ensure that well, and I was thinking about this as far as like context switching and stuff goes, and like multi-threading, like when we have race conditions, just having a counter is not gonna, like, I mean using like a queue or something that is thread safe is not actually going to like fix your problem, right? Because whenever you're locking a thread, like the first one that gets the lock, I don't know, like I don't exactly understand, like if someone has a lock. So I was thinking about this, like the timestamp, even when there's multiple threads, perf counter ns is like so accurate that it will tell you which one came first out of like 3 threads, even if they're like really close to each other. As to where, let's just say you weren't using the perf counter ns and you were just using a counter, like a shared counter, or yeah, like a shared counter, and you executed an action on one thread, and then on the other 2 threads, like immediately after, you also executed a similar action that accessed that shared counter. But since you have a lock implemented on the counter for that action, the first thread acquires the lock, and because it was first there, but now here's the question: who gets the lock after the first one? Like, like, is it the is it the guy who got there first? What determines that? So let me ask, because that's something I don't fully understand, and that was a question that I had about this whole ordeal. But now here's the question: who gets the lock after the first one? Yeah, that sounds so much better. The audio, this mic is like a pretty good mic, and the webcam mic is pretty horrendous. It's like a last ditch, if you're extremely poor and you just have no other option. Yeah, that sounds so much better. So that's cool. Anyway, so let's go to ChatGPT, because ChatGPT seems to be a lot faster than Gemini. And let's say Python, when you have 3 threads accessing the same lock and the first thread gets it first and the other 2 threads are trying to acquire it, which of other 2 threads gets it first? The one who attempted to get it first? Or is it arbitrary? When multiple threads are attempting to acquire the same lock in Python, the order in which they acquire the lock after it is released. When multiple threads are attempting to acquire the same lock in Python, the order in which they acquire the lock after it is released is generally arbitrary. That's not good. That's not good. This behavior is dependent on the underlying operating system's thread scheduling mechanism. Behavior is dependent on the underlying operating system's thread scheduling mechanism. To elaborate, first thread acquires the lock. When the first thread acquires the lock, the other threads will be blocked and waiting to acquire the lock. Releasing the lock. When the first thread releases the lock, the operating system will determine which of the waiting thread gets the lock next. Arbitrary selection. The thread that acquires the lock next is not necessarily the one that attempted to acquire it first. See, now that's a problem. That's a problem. I was hoping that would not be the case, but operating system's thread scheduling algorithm, which can be influenced by factors such as thread priority, CPU time slices, and system load, will decide which thread gets the lock. In most implementations, this means that from the perspective of the programmer, the selection can be considered arbitrary or non-deterministic. Here's a Python example using the threading module to illustrate this behavior. Okay. Yeah. Okay, so that is well, okay, well, then that kind of like suggests that oh damn, like how do you So you can't rely on a you actually can't rely on a lock to solve race conditions. Um, yeah, you can't actually rely on a lock to solve the race condition. You have to like well, I mean, it solves a race condition, but like in terms of like a shared counter or whatever, then you know, that would like let's say the second thread actually got to the lock first, but the third thread acquires it. So that would mean that the second lock would have an earlier timestamp from perf counter NS's perspective, like and in reality, but it would be the next one to on the counter, apply counter. You know what I'm saying? And that would not be right. That would be, you know, bad. That's wrong. It should be, you know, the other thread that gets to be next in line for the to apply that piece of that data change. So anyway, like as far as what we're doing, and as far as solutions for what we're implementing, there's actually like two stages to this problem. First stage is actually that the change attribute list. We realized that it was a race condition vulnerability, and we have to figure out a way to solve that race condition issue. Now, let me think about this for a second. So, because that solution determines this solution. So I can't really like work on stage 2 until I've solved stage 1, and I was kind of just trying to skip stage 1, but I can't actually, like I have to figure this out first. At least I think I do. So I actually like that. Yeah, we have to fix this first. So we have race condition change attribute list. Realizing there is not possible. There is a race condition. Concerning change attribute lists. Aren't they handled through the main thread but also XMS? Yes, they are. So they are handled appended to through the main thread but also accessed and modified on the client threads. Yeah, so I'm pretty positive that is a valid concern. And then after consideration, quite sure they are modified by main thread and client threads concurrently, not only accessed but modified as well. Yeah, so yeah, they are. Like, they are. Couldn't, and then so it's a possible solution. Couldn't we create 3 different lists, one for each thread? Okay. So currently what happens is we have the change attribute list. Let's so the main thread accesses the change attribute list, and then when the main thread is running, it accesses change attribute list whenever it appends the timestamp values and stuff to that. And then in dir check, we are accessing that same list and then but like, when do we access it and how often do we access it? Well, we access it whenever we check to see if there's data that needs to be applied, and in the case that there is data that needs to be applied, so let's just say it detects that the change attribute list is populated, and let me actually pull this code up. So let's just put changed attribute. And we're gonna be looking in server. Let's see. Okay, so we have that's for. I hate how VS Code does that, dude. It always goes to the right. Like, why doesn't it stay to the left? Why is that not like automatically a thing? Why does it do that? It's just bad. Like, it's so bad. That's such a pain in the ass. Anyway, I'll just do it like this. So we have the while true receive, and let's just, we don't want to look at the receive. We're gonna look at the send, because receive is not the problem. It's send. So we'll minimize this reconnect section. And alright, so this is the send section. So here, so as you can see, right here, at this point, this is our race condition vulnerability spot, right here. Whenever we create a copy of this, technically in the main thread, it could be, you know, in the middle of like appending data, and I don't know, maybe a part of that data is there, or maybe some of it is there. I've never actually like seen it get quote unquote corrupted, and I don't know if that's possible. I mean, I like for it to have a part of a data entry in it. I don't really know exactly how that works, but like I don't actually know if this is actually a race condition. Like, I know that we're accessing the same object, right? Like, this is, you know, this is the same object. And of course, like, we have to, like, I was thinking maybe we could create an intermediate attribute list. Like, it goes to the change attribute list when the main thread appends the data change, but then actually after that, it would just like, it would just append that same data to this intermediate list. And if we're going to access that intermediate list, like, we're still going to have the same problem. It doesn't fix the problem. Yeah, it just doesn't. Like, you could maybe, you know, wait till the length of the attribute list got to a certain length. But like that's inefficient. That's not how we want to operate. That's just like, no, we're not doing that. So then like the question is, do we actually have a race condition, or is it just a vulnerability? Like basically what I mean, not basically, precisely what I'm asking is, does the change attribute list being copied right here cause like it, whenever we make this copy, could we somehow copy like data that's corrupted, like unfinished, like a partial append? You know, I don't know the how. That's like deep computer science question. That's like a very zoomed in. So let me ask Python, if one thread is appending to a list and another thread is copying that list at the same time with no lock in place, could this copied list contain corrupted data? I'm sure he's gonna say yeah, but like, yes, if one thread is appending to a list while the other thread is copying that list at the same time, without any locking mechanism, the copy list can contain corrupted or inconsistent. This because list operations are not atomic. In concurrent access with, okay, so list operations are not atomic, and I need to ask him, what does he mean by atomic? What do you mean by list operations not being atomic? So appending to a list, when one thread appends to a list, it may need to allocate additional memory. Appending to a list. When one thread appends to a list, it may need to allocate additional memory if the list's current capacity is exceeded. This operation involves several steps, including possibly resizing the list and updating internal pointers, okay, which is what would happen. And then copying a list. When another thread copies a list, it reads the list contents. If the list is being modified simultaneously, the copying thread might read an inconsistent state of the list. For example, it might read a partially updated list or encounter data that is only partially written. The outcome could be a copy list that contains partial corrupted data. Okay. Gotcha. Okay. So what do you mean by so shared list and then third to repeat the copies? Shared list present link without a lock things. Modified rules being copied. Okay. And I mean, that's no big deal. If I just have to use the lock, like that's you know, that lock's not going to be used very often. But anyway, let me ask about this. What do you mean that list operations are not atomic? In the context of concurrent programming, an operation is considered atomic if it is performed as a single indivisible step. Okay, right, yeah, like, and that's what I was thinking. Like, it either is or it isn't. It either is or it's not. If it's atomic, it either is or it isn't. It's either in or it's not in. There's no like in between. This means that no other thread can observe the operation in an intermediate state. It either sees the operation as completely done or not done at all. When we say that list operations in Python are not atomic, we mean that these operations consist of multiple steps that can be interleaved with steps from other operations if proper synchronization is not used. This can lead to race conditions where the final state of the list depends on the exact timing of the operations, which is generally unpredictable. Checking the current capacity of the list, allocating more memory if necessary, adding the new element to the appropriate position, and updating the list internal size counter. Ah, okay. Okay. These steps are not executed as a single indivisible operation. If a thread switch occurs in the middle of these steps, another thread could observe an inconsistent state. Okay. Reading the size of the list, allocating memory for the new list, iterating over the elements of the original copy to the new list. This is not thread has been used this while another is coming there might see parts updated. Okay. Okay. So what we're gonna do is I'm gonna go ahead and side with even though it's probably unlikely, you know, it's still possible. So I want to get rid of all those sort of possibilities because, you know, with debugging, I don't want to think there's a bug in my code somewhere else when it's really just a very rare intermittent data transfer issue, because those are by far, I think, the nastiest bugs and the hardest to solve. So I think like it's the most important to just like when this game was what wasn't an online game, when it was just like a regular single player, involving no server client relationship, no like data transfer, it was easy to debug, man. Like it was, I mean, when I was first started, it was still hard for me because I was new to programming, but comparatively, it was nothing. It was so easy, like so easy. But when you're dealing with race conditions and all this stuff and latency or like delays and, you know, all that, it can get really ugly. So yeah, we're gonna go ahead and I think probably implement a lock here. So like we'll just create like oh yeah, and here's another thing. I realized this yesterday. Below data structures, in case of DC, when threaded client is run again, it will recreate these lists which may have still been populated, causing these lists which may have still been populated, causing data corruption. Okay. Or not data corruption, data loss. Okay, so need to convert to server attribute. Yeah, buddy. Okay. Attributes. Now. Okay. So I guess, like, you know, do we need the lock to be like a server attribute? I mean, I don't think, like, but I was thinking, what if one thread like acquires the lock and doesn't release it, but that would be handled by with the context manager. So as long as we used with, then it would always be released, even in the case of like an exception. I'm pretty sure that's the whole purpose of the context manager. So let's say Python, if we have a lock on one lock acquired on one thread, and then an exception is raised if we use the lock using with as a context manager, would that ensure it gets properly what is it called, released after the exception? Yes, using a lock with the with statement as a context manager in Python ensures that the lock is properly released, even even if an exception is raised within the block of code. The with statement guarantees that the lock is released when the block is exited, regardless of how the exit occurs. The block is exited regardless of how the exit occurs, normally or via an exception. Okay, so like, what if the thread that's running it completely terminates? But what if the thread that was going to release the lock crashed before it got released? That part of the code. If a thread crashes before it can release the lock remains acquired, potentially causing a deadlock situation where other threads are blocked indefinitely waiting for the lock to be released. In Python's threading model, there is no built-in mechanism to automatically release a lock if the thread that acquired it crashes. This is because the lock is a low-level primitive, and the runtime does not keep track of which thread owns which lock. Thread owns which lock. To handle such scenarios, you can use a higher level constructs or patterns that provide more robust handling of thread termination and resource cleanup, such as using try. Finally, ensure that locks are released even in the case of exceptions. Thread is able to terminate outside of the control due to system level failure. Using a timeout. When acquiring a lock, you can use a timeout to prevent indefinite blocking. This way, if a thread holding the lock crashes and never releases it, other threads won't be blocked forever. Okay, that's cool. So that's a good. That's actually like a possible solution, is doing that. And then 3 is using a rlock or condition. These higher level synchronization primitives can sometimes help manage more complex locking scenarios. Rlock or condition. Oh, they don't solve the problem of thread crashes directly. Okay. Internal watchdog. Implementing an external watchdog that monitors thread health and restarts threads if they are not responding might help in a long-running application. Okay. Monitors thread health and restarts threads if they are not responding. Okay. Here's an example using a timeout when trying to use with lock. Simulated crash. Finally, print crash. True, acquired, lock, acquired, and then timeout is 1. Okay, so then there cannot acquire lock. We'll try again. We'll try again in a second, I guess. Like in 1 second. And then choose lock first. Wait for the to complete. The period tries. However, mechanism have prevent the second thread from being indefinitely blocked so it crashes. This approach can help with scenarios with lock might not be released properly. Okay, so yeah, there's the timeout scenario, which I mean, like, let's think about this. So if we had we have a like if we added in a timeout, I was just thinking about like a weakness to the timeout, like in the case where the action, you know, you give it a 1 second timeout or 2 seconds, whatever, and you know, it's not actually completed within 2 seconds for like whatever reason. So that would be an issue, like in couldn't you add like a I was gonna say, like, couldn't you add in a custom, like a custom timeout thing? But okay, so I guess the real question would be if there was a, you know, valid reason that, if there was like an actual reason that it might take longer than, you know, 2 seconds in some sort of instance for that execution to finish, and like copying is basically instantaneous. It takes virtually no time at all, like a microsecond, you know, or something. It's so fast. And the other action that gets that happens to it is this is there's a for loop. Let's see, so we have the alright. Well, actually, okay, no, yeah, we iterate through the change attribute list, and then we do remove certain entries. So well, actually, hold up. Is this is for send, right? Start second send section. Yeah, if length of current for 2 in the change attribute list. Okay, so all we did was copy it, but I mean, then we end up okay, we say associated change attribute list. Alright, so where's associated change attribute list? That's the one we're looking for. It's definitely used again. Oh, I think I just realized a bug here. Where it says, so if current client ID is equal to 1, we say current client change attribute list equals C1 change attribute list copy, and then associated change attribute list C1 change attribute list, and
welcome, Harry, to Diagon Alley.
yeah, but then we sign associated change attribute list equals C1 change attribute list, and then we do the same thing if client ID is equal to 2, current client change attribute list equals C2 change attribute list copy, and then associated change attribute list equals C2 change attribute list. And then if length of current client change attribute list is greater than 0, okay, Then we iterate through the change attribute list, the current client change attribute list, which is the copy. We run dir check, and then we remove it from the copy. But that doesn't actually remove it from the actual list, from the actual change attribute list. But like, shouldn't we remove it from the change, the actual change attribute list as well? Shouldn't that be a thing? I think that should totally be a thing. Because yeah, I mean that just, like, if we're not gonna send that data point at the time that it was supposed to be sent, then that means we're not sending it. So that means, you know, the actual change attribute list should be depopulated along with the copied one. So yeah, this I'm pretty certain needs to be removed as well. But don't we just remove all the elements that but it iterates through the, hold on, let me see. The current line change attribute list is greater than 0. Data pickle down. Where's this one that I'm looking for? The associated change attribute list. That's what I'm looking for. Okay, here we go. Alright, and then we iterate. Let me slow down, go in order here. So we assign current client change attribute list to the copy of the actual change attribute list. Then we create a pointer, a reference to the actual change attribute list, which is called associated change attribute list. Then we check to see the length of the copied list. If it's populated, we then iterate through that copy and check to see if there's anything that needs to be removed, anything that we actually don't want to send. So if there's anything we don't want to send, we then remove that from the copied list, but it remains in the actual list, which I'm pretty sure is a problem. Let's keep going to verify that. Then it checks if the length of the copied list is greater than 0, meaning it's still populated after we've removed, you know, the entries that don't need to be sent or won't be accepted for whatever reason. At that point, we say data equals pickle.dumps. Then message head. Then connection.sendAll. Okay. And then other con send all. And let me make sure I'm using send all instead of send versus send all. 52224. Ensure we are always using send all over send since it's safer. I'll have to look that up, but anyway, I don't want to get too sidetracked. So it checks to see the length of the copied list, and if it's populated, it will iterate through the copied list and remove anything that needs to be removed from the copy. Then it will create the data based on that filtered copied list. If its length is greater than 0, then it creates that message which contains the change attribute list copy. And then it handles this timestamp thing, and then it's it goes for toop in current client change attribute list. So this is the line we're looking for. So then it iterates through the copied list and it removes each entry from the copy from the actual. But here's the problem. Even though it removes all of the ones that exist at this point, it still didn't remove all of the all of them, like in total. It didn't remove them all, and we actually need them to be all removed. Basically, anything that is copied needs to be removed. So, like, couldn't we just do right after this if right here? Couldn't we then say, go ahead and delete all the ones? Couldn't at this point we would delete all those entries from the actual that are in the copy? So my only concern about that is if there is like a there's an interrupt to the if it gets interrupted, like let's say C2 associated change attribute list is assigned to C1 change attribute list, and then we create a copy of the C1 actual, and then we delete everything from the actual C1. But before we actually send the data, something happens on the threaded client on the server side that causes it to crash or whatever. Something goes wrong. Some exception occurs, and at that point, even if we restarted the process, the actual C1 change attribute list would be gone because it's already been depopulated. So I guess it would be a little bit safer to remove them after we sent it, because that would just avoid that problem. You know what I mean? Like, that would just avoid that. And you could say technically, well, the same issue exists there, but like the time span between the two is a lot smaller if it's happening like right next to each other versus it's getting deleted up here and then we send it way down here, to where there's like this gap between where that error could occur, and then it's then the error happens. So let's not put it up here, and what we'll do is we're just gonna I'll put it right here. Well, whenever it removes these, we'll put associated change attribute list dot remove and then 2, because obviously we don't want it in that one either, because that's the actual. So we'll put removes 2 from actual CL, and then this one removes to from copied CAL. And then down here, after we send it, that's when we oh, you know what I realized too? I don't think we actually, well, no, we don't, yeah, we don't have to, we don't have to clear the current client change attribute list because it gets recreated each time. So I was going to say we should remove all the values from the C1 or C2, but since we're reassigning it right here, that, you know, like there's no way for old values to get reused or whatever. As far as like it being a memory thing, we don't want to store memory. I mean, it's virtually no memory, so like, you know, whatever. I don't think that would be a concern. So I do realize though that I don't know why we wouldn't do this first after we send. Then we can do this first timestamp thing after. Like we should do the send, and then immediately after we send it, that's when we should clear out that change attribute list. So then we have removes all tubes from in copy from actual CL. Yeah, buddy. All right, that's good. Now, alright, so this associated change attribute list is the actual list. So we have to make this be, we have to avoid that race condition, remember? And technically, this is a race condition. Associated change attribute list equals C1 change attribute list. Okay. And right here, this is when we remove a tuple from it. And then right here, we remove tuples from it. Well, and then we also access it when we create the copy. So these three places need to have a lock. We'll put use lock, and then right here. We're gonna want to use the lock there. And then here we'll use the lock, and I think that's it. Okay, so how do we do this? Are we gonna have a lock? Are we gonna recreate a lock? I mean, the lock has to be accessed by the multiple threads, so it's gotta be like, it's gotta exist. It's gotta exist on well, I was just thinking about this. Like, if we have a threaded client, well, yeah, because it's a local function. Then it would be. I mean, then it would be a local variable. So there, if we assigned it within the threaded client function, the main thread and the other threaded client thread would not have access to it. So it would either have to be created in the main thread and passed in as an argument, or we could just have it as a class attribute, or an instance attribute rather. So I guess I'll go with the instance attribute thing. And I don't know how many locks we're actually gonna need. This is like the only one I can actually think of right now. Let's say, let's go over here, and we will create this new lock, and we'll say self.cal, and that equals, don't we have to import lock or something? Python lock. So lock segregation primitive from threading module. Okay, so it's from threading. It's used to control access to shared resources by multiple threads. If a thread acquires a lock, other threads that try to acquire the same lock will be blocked until the lock is released. Here's a basic example to demonstrate how to use a lock. Okay, so we say import threading, and then T threading start append start append T start. Okay, where's the lock? Okay, with lock. So lock is just equal to threading dot lock. It's that simple. And in that case, we don't have to write out lock dot acquire or lock dot release. We could just say with lock, execute this line. And then we'd pass in the timeout arg to be like, I don't know, 3 seconds or something. I'd say like 3 seconds should be fine. 3 seconds should be plenty. So this will be threading.lock. Is it capitalized? Yeah, it's capitalized. So threading.lock, and then we just say with use lock. All right. So then we would just do with self.cal lock. Do this line. Avoids race conditions since this is accessed multi-thread. Same thing here. We're just gonna copy and paste at this point. And We actually need to do both of these lines because that's so we're accessing the actual change attribute list right there, and then we're accessing it again right here. So yeah, technically both of these are like accessing. Yeah, like if we're gonna even just copy it, like it's still gotta, you know, and that's just a basic programming question I don't really know the answer to. Let's just say Python, when you make a new list equal to an existing list, what exactly happens? Background. Is it an atomic action or multiple steps? You make a new list by using the equality operator in Python. Okay, I'm sorry. I messed up wording that. You're not creating this, rather comparing two lists together equal. On the other hand, if you create a new list that is a copy of the existing list, there are multiple steps involved. Okay, yeah. Okay, yeah, no. That's not. Let me frame this Python. If I assign a new reference pointer to an existing list that is used on multiple threads, could that be a race condition vulnerability? Or is assigning a reference pointer a thread safe action? Assigning a new reference to an existing list in Python is generally considered to be a thread-safe action in itself. This is because the assignment operation for references is atomic in C Python, meaning that it is executed as a single indivisible step. However, this does not mean that your code is free from race condition vulnerabilities. When you assign a new reference to an existing list, Python essentially updates the reference count for the list object. This is an atomic, so it updates the reference count for the list object. This is an atomic operation in C Python. Okay. Well, the assignment itself is atomic. Race can occur in scenarios where multiple threads are assigning references. Yeah, yeah. It's not so much that action is not thread safe, it's the fact that the other action is, is not atomic. So yeah. Concurrent access and modification when there's okay, yeah, so that was a little bit, not necessarily a dumb question, but I should have realized that. Anyway, current client change release. Alright, so yeah, we do need to involve this assignment in the lock. And I'll just put this must be in lock process because other threads actions on this list are non-atomic. Okay, so now let's go to the next use lock. And then let's put width. Oh, but that means we have to add in logic for the other place to acquire it. Yeah, I almost forgot about that. Okay. Now I need to add in
You have your mother's eyes.
finish adding in server dot cal lock. Is that what it's called? Yeah, that's it. Self.cal lock. Okay. All the places where actual CALs 1 and 2 are accessed or modified. Okay, yeah, I'm gonna take a little break. Just a tiny one. And I'll be back in like 5 to 10.
Consolation to creatures unity.
You're more like time will come to say just how much.
Welcome, Harry, to Diagon Alley.
Okay, that was a way longer break. I had to take care of something. So that break was fucking long, like really. Okay, anyway, so we're back. Let's try to do. Damn, that was like a 20-minute break, dude. Damn.
To keep his friend Harry Potter.
Okay, so now let's finish the so we have to finish that, and then we can so like I was thinking, actually, hold up, kind of jumped the gun with the lock thing. Couldn't I use a queue? Like a queue is basically like a storage data structure that uses locking, and like, should the change attribute list just be a queue? Like that would, to where I wouldn't even have to, you know what I mean? Like I wouldn't have to say with self.cal lock, etc, etc, etc. Like it probably might be less overhead too. Well, I don't know about that, but I don't know. Let's see. When should I use a queue instead of lock? Using a queue instead of a lock is often beneficial in scenarios where you need to safely communicate or transfer data between multiple threads. Here are some guidelines to help you decide when to use a queue. Oh, right, because that allows the thread to continue working. But like, well, that's if there's multiple things adding to it, like, or taking away from it, if you will. But in this case, it's never being removed, like it's never being popped from. It's only being appended to on one thread. Well, actually, remember we were talking about how this works with how we were going to implement the But like, so a queue allows you to modify allows itself to be modified multiple times, like concurrently, and it doesn't block I don't think, you know, like you can go to add it to the queue, and then whenever it's ready, it will add in that value instead of you like waiting for it to be available to add in that value. But since we're only like modifying it from one place, the main thread, well, no, we're removing from it. No, yeah, we're removing from it, duh, in the other thread. So in this case, maybe maybe we should use maybe we should use a queue. Let me think. Use a queue instead of like some beneficial scenarios where you need to safely communicate. Use a queue when producer-consumer problem. If you have a classic producer-consumer scenario where one or more threads, producers, are generating data and one or more threads, consumers, are processing that data, a queue is the perfect choice. It handles synchronization for you, ensuring that data is safely transferred between threads without the risk of race conditions. Yeah, but how does that like work? How is it synchronized? Like, how does that? Decoupling threads. When you want to decouple threads so that they do not have to run at the same pace. Producers can put data into the queue at their own pace, and consumers can take data from the queue at their own pace. Buffered communication. If you need a buffer between threads, such that the producer can continue working even if the consumer is busy or slow, the queue will store the data until the consumer is ready to process it. Thread safe data transfer. You need a simple thread safe way to transfer data between threads. You need a simple thread safe way to transfer data between threads without manually handling locks and synchronization. The queue handles all the necessary locking internally. Okay. Ryan, range of 5. Thread synchronization in Python involves coordinating the execution of threads to ensure that they can safely access shared resources without causing data corruption or inconsistency. Synchronization is essential in multi-threading environments to avoid race conditions, deadlocks, and other concurrency-related issues. Key concepts of thread synchronization. Critical section. A part of the code that accesses shared resources must not be executed by more than one thread at a time to prevent race condition. Key concepts of thread synchronization. Critical. So rlock allows the same thread to acquire it multiple times, useful for recursive functions. But like if anyway, semaphore allows a fixed number of threads to access the resources at the same time. Event, a flag that threads can wait for, can be set, cleared, and checked. Useful for signaling between threads. Condition, a more advanced primitive that combines a lock with a signaling mechanism. Useful for complex synchronization patterns. Q, a thread safe FIFO data structure that can be used for communication between threads implementing the producer-consumer pattern.
You're a wizard, Harry.
Okay, so an event is basically like a lock. Sort of like the inverse of a lock. It's like this thread will wait until the other thread says you to go, instead of this thread will go and the other one will wait. trying to think of how queues, like, how do queues work in the background to execute synchronization. Queues in Python such as queue from the queue module provide a thread-safe way to transfer data between threads. They use underlying synchronization mechanisms to ensure that multiple threads can safely access the queue without corrupting its contents or interfering with each other. Let's delve into how queues work in the background to achieve synchronization. Queues use locks internally to achieve synchronization. These locks ensure that only one thread can access the queue at a time, preventing race conditions and data corruption. Put and get. Put item. When a thread puts an item into the queue using the put method, it acquires the internal lock. When a thread puts an item into the queue using the put method, it acquires the internal lock. This prevents other threads from modifying the queue simultaneously. Get. When a thread receives an item from the queue using the get method, it also acquires the internal lock. This ensures that only one thread can remove an item from the queue at a time. Blocking and non-blocking operations. Blocking operations. If the queue is empty and a thread tries to retrieve an item, get, it will block until an item. If the queue is empty and the thread tries to retrieve an item, it will block until an item becomes available. Like, it will block. Okay, I see. So it's like a while loop, like on that thread. Similarly, if the queue is full and a thread tries. Similarly, if the queue is full and a thread tries to put an item put, it will block until space becomes available in the queue. Okay. Non-blocking operations. Queues also provide non-blocking no wait. Get no wait that raise exceptions queue full or queue empty instead of blocking when the queue is full or empty. Thread safety. By using locks internally, queues ensure that all operations, put, get, etc. are thread safe. Only one thread can perform an operation on the queue at any given time, preventing concurrent access issues. Okay. Queue for I and range. Q.put I. And the consumer is item dot equals q.get, and then create producer and consumer threads. Okay. And then producer thread join. This example, the producer function puts items into the queue. Are queues a lot slower than lists? Queues and lists serve different specific purposes. Their performance characteristics different from the lists we use are highly optimized for random access and manipulation. Queues such as queues will be done for inter-thread communication to provide thread safety overall performance. In the performance example he gave above, what are the results? Okay. So I still have to figure out if I can actually use, like if I should use a queue for the change attribute list. Um, and actually, I'm just like really tired, honestly, right now. I can't really like focus very well. I didn't sleep very good last night at all, as usual. And you know, it sucks, but it is the way it is. And I also got a really late start, so like I don't want to drink coffee or anything that would wake me up this late in the day. So I'm just gonna like take the L and just finish. Go ahead and wrap it up for the day. And let's see, let me just work on this for a couple more minutes. So if we were to just use a lock instead of creating a queue, like what, like I'm trying to think. So a queue, I don't really understand this completely. Does a queue allow an element to be added, put like, well, no, it's gonna, so okay, so I understand. It's basically just waits. I see. Like it's not that you can execute simultaneous activities on it, but like, does a queue allow an element to be added at the same time? At the same time, another thread is putting an element in it. Like, I'm thinking of it as like a buffer, basically, where anyone can come and just like put stuff on it, like, or does it like block throughout this process? I just don't have a good understanding of it. On queue implementation, the put method is thread safe, meaning that multiple threads can call put simultaneously without corrupting the internal state. However, the queue's capacity may still impose limits on simultaneous put operations. Here's how it works. The queue class internally. Okay, yeah, we already know that. Okay.
Fascinating creatures.
Queue class lets you specify a maximum size for the queue. If the max size is not specified, queue size is unloaded. If max size is specified, the queue will block when attempting to put an item in the queue is already full. If the queue is full, the put will block its space. Okay, yeah, so it's like it's not truly simultaneous. But like this basically means that like what's the difference between using a list with a lock and a queue? Like what's the real difference? What's the real difference between using a queue and using a list with a lock? The difference between using a queue and using a list with a lock lies in their intended use case design principles. Queues are specifically designed for inner thread. Okay. Yeah, I get all that. Yeah, I know that. Okay. Use and safety. Queues offer a high-level convenient interface for transferring data between threads. They handle internal synchronization transparently, make it easier to write thread safe code without worrying about low-level synchronization details. Okay, yeah, so queues are really specifically for the if you're not sure if the queue, like stuff is getting put in and then something else is taking it out, not and like when you go to take something out, you don't know if there's anything in it. Like it will guarantee though that that action happens and is nice and smooth. Okay, that gives me a more like a better understanding. And then a list on the other hand though, like you're just gonna have to like you would have to manually add in like a block and like while there's nothing in it, while the length is 0, you know, like so. Okay, I see now. Like so, queue is like a very specific thing. Now, like I I don't think like I don't think I actually need to use a queue. I think that I could use a lock with the list. Now, is it actually worth it? Like, can you show results from other people's testing which determines if queues are slower than using a list with a lock? Can't find real-time research results, but I get number insights. Alright, yeah, I already know that. Alright, can you show me someone's test on queue performance versus list? Okay, yeah, alright. Python queue performance versus list with lock. Deck versus lists. That's something I need to learn about. Oh wait, that's it? That's all it says? Linked lists, yeah. So I've heard about these, but I've never really used. You know, I heard like, yeah, the answer is always a linked list. I've heard that joke. So yeah, I definitely need to learn about some of this because when I'm tired, I just can't like really come up with thoughts, but I can take in information and like learn. Not as good, obviously, but it's a lot harder to like construct and create when you're tired than it is to just like watch and take something in. So um, anyway, I think I'm gonna wrap it up for the day, and so let's just go ahead and fill in our devlog, which we didn't really make we didn't really make great progress today. I mean, I'm not gonna lie, I did learn some things, but I still am not like I'm still not sure about, do I really need a queue versus just using a list with locks, because and let's put deck versus the list. I wanted to put this one. So um do I need a deck? I mean, not a deck, a queue. Do I need the queue, or do I just use a list with a lock? Okay, yeah, I'm just done. I'm just like not here. Anyway, so we're not even gonna push or anything. I'll just I'll see you guys next time. Y'all have a good one. Hopefully I'll be more